Okay, good evening, everyone. Thank you for joining us for our lecture series, lecture number 2. I'm really excited to be giving an introduction today for our guest speaker, Dr. Tarek Rakha. I have an introduction I'm going to read because there's so much to cover with Tarek, but I think it's really exciting to highlight some of these achievements before he begins. So, Dr. Tarek Rakha is an academic entrepreneur. He is co-founder and CEO of Lamarr.AI, a startup transforming how buildings are retrofitted through AI-driven diagnostics and design intelligence. He also holds a tenured faculty position at Georgia Tech, where he's an associate professor of architecture and the director of the High Performance Building Lab. Tarek is also a Regent's Innovator, which I've recently learned is a very rare and prestigious title reserved for tenured faculty whose research has been translated into high-impact, commercially viable ventures. This title grants him a leave to pursue scaling of his company, Lamarr.AI, which we will hear about this evening. Tarek's work in building technology, urban energy sensing, and climate resilience has been recognized internationally and nationally with over $7 million in funding, as well as dozens of peer-reviewed publications. And he holds a Ph.D. In building technology from MIT. Some of you may know that Tarek was once a full-time faculty member here at Syracuse in the School of Architecture. And I had the great pleasure of working very closely with him on several research projects, really kicking off some major projects here in the School of Architecture. And it's a real joy to welcome him back as a colleague and friend. Please join me in welcoming Dr. Tarek Rakha.
Thank you so much, Bess, for the wonderful introduction. Thank you, Michael, for inviting me. And hello, everyone. It's very nice to be back. I was last here 6 years ago before moving to Georgia Tech. I have nothing but fond memories. Well, I have some bad memories too, but nothing but fond memories in general in Slocum, so I'm happy to be here. I will walk you through in the next 45 minutes or so my career directions when it came to research, teaching, and more recently entrepreneurship. It's an exciting journey that I'm very happy to share with you. So the title of the talk today is From Studio to Startup, Retrofitting at the Speed of AI, because I learned how to teach studio here at the School of Architecture, and I had a lot of interest in design education. And then moving forward, research became quite a part of my work, and then translated that into the startup that I'd be very happy to share more about. So I'd like to start first by my personal motives. This is an artist's depiction of the United States leaving the Paris Climate Change Accords, the first iteration, which is a representation of how a decision of self-harm can also be harmful to others. The climate change that we are experiencing is the greatest threat in human history, and we really have to be paying attention to it. As you probably know, this is from the NASA climate spiral. We have reached a point of warming in our planet that is significantly disturbing. We have increased more than 1.5 degrees Celsius as of this year, and we continue to experience a warming planet. But on the other hand, there's also the planet that is being measured on every scale. We are in the age of the Internet of everything that we can prioritize to measure, and we know more today about the built environment than we've ever known before in any point in history because of the kind of sensing and technologies that we are using. So there's these two perspectives on the Earth that are happening at the same time. The Earth that is experiencing climate change and the calamities of it, and the Earth that we are sensing and we're collecting data about. The problem is we're typically collecting data and using models and simulations and even AI for communities or populations that we are prioritizing to measure. And so those who would be experiencing climate change in the frontline communities and marginalized communities, which we are not measuring data for, we will be always forgetting them. As you understand now more about AI, it's all about the data that you're training it with. And if we don't know about our most vulnerable communities, we are going to be forgetting them and at the point of abusing these kinds of communities. But we are lucky that we are in the built environment because the design decisions we make have a severe impact. As you know, 40% of carbon emissions are in the built environment, and up to 76% of electricity use goes in decisions in buildings. So every decision you make will have an impact. However, I argue that we are at this very interesting moment of convergence where we have to be shedding our disciplinary differences between architects, mechanical engineers, civil engineers, even communities themselves. We have to be coming together through the specific and compelling problem that is climate change, as well as including community stakeholders and doing deep integration to be able to solve the real challenges of our time. So the statement that I go by in my research directions is climate change is the greatest threat in human history and marginalized communities are the most vulnerable to its dire risks. We must transform climate responsive architectural design decisions to advance both racially and socially just solutions through convergence scholarship. And so you'll notice that in this statement, I don't put AI forefront and center because it's part of the approach of the scholarship, not really the means of the research. So I'm been fortunate to lead the high performance building lab at Georgia Tech, where I have continued research directions that I've started here at Syracuse University. I'll talk to you today about 4 topics, starting with the bread and butter of anyone in my domain, which is building science. And in building science, I really like to promote the teaching goals, which are to create experiential learning endeavors where the classroom becomes a medium that empowers you to have lifelong skills and to utilize these tools that we are using and developing in research to empower frontline communities through design, and finally enhance learning through the creation and testing of equitable design that advances environmentally just solutions. This has been my approach to teaching, and I'm happy to share a lot more about how that started specifically with Studio. Let me say that I started teaching Studio at Syracuse University without teaching Studio before, and I got the best feedback I can ever get, which is I was terrible at it in the first semester. It was, I not just remember the words of the student feedback, I have them printed, because one of them said, "You don't belong at Syracuse University," which was very interesting to hear. And so I went to the other faculty and actually asked a lot about how to teach Studio and learned from them. And then in the next studio, which was Startups in the Desert, that was a travel studio in Dubai, did really well and continued to learn how to teach studios until I came to Georgia Tech and I was able to lead award-winning studios. So I'll walk you through some of the examples of this. This is a design and research studio that won 2 awards, an honorable mention and first prize in the AIA and ACSA's Here and Now competition. This is called Recovery Assemblies that got the honorable mention. It was about deployment of temporary structures in situations of vulnerability, whether it's war zones, etc., that would be self-sustaining, energy generating, as well as shelters for communities that are in transit. So that was a great achievement for that team. But the team that won had a design called Another Life, and they were focusing on the life of a fisherman's life in Iceland specifically, and designing the architecture in such a way that the form responds to the environment, but also we're thinking about energy now. And we're doing comparisons on every month between the base case that is not doing very well in terms of heating, cooling, lighting, and then does a lot better with the design moves. So when you see the architecture with a capital A that is really attractive, that wins competitions, you know because of the simulation tools that students have learned and are using that this is supposed to, and probably will, perform. And the way I typically approach this in teaching is that in the basic building science courses, I teach students simulation tools that we use in research so that they're able to compare base cases with design cases to understand the impact of every decision, and also embed this in ways to empower and inform marginalized communities. For this specific course, the students were working with a community called Grove Park, which I will mention at least a couple more times, where they did simulations for the existing cases and how the daylighting moves that they did enhanced the performance. This is a representation of climate futures for every month and seeing not just the design of how it would perform now, but actually how it would perform in 50 to 100 years. This is the Dubai Travel Option Studio. This was one of the best experiences in studio teaching in general. Michael will recall that there was funding that allowed the students to travel to Dubai, and we've interacted with multiple practices, learned a lot about the architecture of the desert. But the very interesting thing is, I didn't know this at the time. The studio was called Sustainable Startups in the Desert. I didn't know I had an interest in startups ever since then. So it will be very interesting to show you how the startup is performing later. But as you know, Syracuse University students are amazing in terms of visualization, representation, articulation of architecture, and going through all of the design thinking that translates into impactful visuals and impactful design decisions. What my role is in such design setups is to empower students by using the visualization tools to represent environmental design. This is specifically daylighting design, for example, for the before case, where they were building a building under the ground to use the terrain and use underground energy sources in the desert environment. And then there's no daylighting happening here. So what they did, like slits, atria, courtyards, all of the moves to increase the daylighting performance and showcasing the before and after of that. So I'll bring this to the second topic together with building science, which is community analytics. And that ties very well to the research goals that I typically lead. I would love to transform climate responsive design decisions to advance both racially and socially just solutions, develop and deploy novel robotic, sensing, simulation, and AI technologies to address the climate crisis. And very important for me is to establish impactful collaborations. I never want to work in silos. I always want to work with government, industry, and academic partners, because in order to see impact, you have to be building relationships with those decision makers as well as those who are experiencing the research decisions that we are making. So I did my Ph.D. at MIT, and this is the urban modeling tool called UMI. It's still active until today. I was focused on the walkability and thermal comfort of outdoor spaces, but this is the citywide energy study of Boston for the part of the MIT campus represented here, to see the energy flows of campuses and multiple buildings and how we can understand design decision processes at that scale. So this project is called Community Energy, Technical and Social Challenges and Integrative Solutions. And of course, this was a collaboration with Bess. And I'm so sorry, Bess, this is not my design, but the screen is not doing your picture a favor. We worked with a community called Muller in Austin, Texas. This is an affluent community that installed renewable energy, had high performance glazing, and really well-oriented buildings, etc. They had a great interest in how their energy performance and carbon emissions are. And so we worked, we were funded by the National Science Foundation, and we worked with partners like Pecan Street, who I'm still working with until today, partnered with the Syracuse Center of Excellence, etc., to understand the energy flows of that community and how we can help them in making decisions. So in terms of how that looked like from an energy modeling perspective, this is what's called an urban building energy model. It's a representation of the energy flows across 300 buildings. And in terms of design, basically all of the moves that you can do to perform better from an energy efficiency perspective, whether it is using daylighting or changing the settings for HVAC, or changing not just the set points, but also the equipment power, etc., using natural ventilation, and comparing the performance of the existing case of the buildings and seeing how these decisions can lower the impact on an energy use perspective, which is great for a community that is attuned with what their energy goals are and how they want to be much more sustainable. But here's the catch. I've been talking about marginalized communities, and this is not an example of that. This is actually a very easy example, because they want all of their buildings to have sensors. They want to understand at the circuit level what is the fridge performing like? And so this is where another research question came through, which is fairly straightforward. What if we are in a community that we can't measure? And what are we not seeing when we can't measure data? So I was really motivated by the Black Lives Matter movement with the murder of George Floyd at the time to think about inclusivity when it comes to building physics and building science in general. And I would like to showcase to you the kind of work that we've been doing when it comes to that, and that's specifically working with frontline communities. Because such communities have less likelihood to have available data, will have limited resources to generate and maintain data, and will have challenges in data collection and communication and priorities, all of it. And so I worked with one of our students at Georgia Tech on a project that was not funded called Underrepresentation Challenges in Urban Building Energy Modeling, where we were defining archetypical inputs for that kind of urban scale, understanding from the US Census Bureau, the American Housing Survey, residential energy consumption directs, et cetera. How can we scrape the data that we can have access to and collect our own as well? So this is Grove Park that I mentioned earlier. It is a 98% African American community with a median income that is less than $25,000 annually. So it is a community that will be facing climate change very differently. This is a representation of the setup of 100 buildings where you can see the variance. There's good conditions, excellent. Actually, there's vacant lots, there's poorly performing. And so translated this to an urban building energy model and started to understand what the inputs would be so that we can do comparisons between what the model would say if it is not calibrated to the real conditions and if it is. And what you're seeing here vaguely is this is the typical UMI model of performance of energy over 12 months of a year. The purple is the typical inputs for the PNNL, the Pacific National, Northwest National Lab inputs. And the calibrations look severely different, as you can tell. So if we're making decisions using simulation tools and we're not calibrating them for the realities of underserved communities, we really are building a virtual thing that would not work. And that's really the lesson that's learned here, developing inclusive urban and building energy modeling inputs for equitable resilience. And so this was a great motivation in most of my research when it came to urban scale thinking. The first research project I showed you was with Grove Park. I also worked with Thomasville Heights, which was building strategies for energy efficiency retrofits. This is a community that we were embedded in and actually have had budgets to upgrade and retrofit at the scale of $2,000 to $3,000 per building. And so the impact was severe, at least from my perspective, because I've never had someone come up and say in that kind of community meeting, this research changed my life. Our building is actually more comfortable now and the energy bills are lower. I can publish 10 papers and it will never have the same feeling of someone saying the research had an actual impact. And so you can see from that quote, making utility bills affordable and making the house warmer when it needs to be, etc. Also, there was another project called Building a Sustainable Mobile Learning Lab for the West Side neighborhood, where the students were working on the design of a mobile lab that would be an energy generator on its own, but also has features of education when it comes to sustainability. But the project that I'm really, really very proud of is English Avenue Yellow Jackets. That is the solar decathlon design competition that this team won, not just the retrofitting housing design category, but also the entire competition. So the solar decathlon is a competition that is national and international that focuses on energy efficiency for housing in general. They had a new category called retrofitting. And so 3 students came to me and asked me if I can help them in leading a project. And I said no, because I was up for tenure. Bess will know. I was up for tenure, and I was like, nope, can't do that, have to focus on papers. And then they said, please. And then I said, okay. And when they won the competition, it really justified everything. But this is a 102-year-old home that's existing in Atlanta that the students surveyed, worked closely with, understood all of the challenges and the really unfortunate condition that it's in, and devised an approach for learning from the community members themselves what the situation is. There's no audio here, I'm just showing you that they interviewed the community. And designed a roof that is loaded with all of the tools for resiliency, whether it is rainwater collection or the tilt for PVs, etc. This is the team in action, actually. This is the High Performance Building Lab. And actually, they designed a net positive home. Unfortunately, the number that's showing here is like it's positive by 3 kBTUs per square foot annually. But basically, the home generates more energy than it uses, and therefore you can sell it to the grid, get that money, and use it on anything that that community or these household members would want to use it for. This is the team. It's comprised of architects, high-performance building students, as well as masters in real estate and building construction in general. And the student in the middle is actually in industrial engineering, but she had a background in building performance. And so the impact of this is that we made a model for retrofitting that is based on the means of upward mobility of an underserved community. You can take a derelict building and upgrade it in such a way that it becomes the means of prosperity if we are putting in enough of the sustainability techniques and aspects and technologies. Okay, I'll go to outdoor thermal comfort because it's very relative to Syracuse. This is the topic that I was focusing on my PhD. This was towards comfortable and walkable cities, which were 4 years of significant impact on my life. I was depressed. I came to Syracuse overweight. I used to look very differently, but the PhD has that impact on you, and I'm so glad that I went through it, but I wouldn't do it that way again, to be honest. This is Comfort in Motion, which is a class I taught at Syracuse and also taught at MIT, where the goal is to create the spaces in between buildings as a comfortable but also vibrant, multimodal, bikeable, and attractive kind of activity spaces. And focusing on outdoor thermal comfort is interesting because we are making decisions every day about our comfort, what we're wearing, how we're walking, what kind of transportation mode we will be using. And so using simulation tools to showcase that is quite interesting in the context of urban scale thinking. However, the first project I ever got funding for, and Michael will remember this as well, is called Fast Syracuse, which was funded by NYSERDA and the New York State Department of Transportation. I applied for funding from with the Syracuse Center of Excellence, and we got selected for the funding before I joined Syracuse University, so it was a great beginning. And through it, applied all of the things I've learned to develop these spatially resolved thermal comfort maps so that you're able to identify where to place a coffee shop, how do you place a bicycle track, all of these decisions when it comes to the urban scale as it relates to comfort. And interestingly, we had a really great turnout for the final event where we got feedback from everyone. You can see faculty, and Michael was there as well, and members of the Downtown Committee of Syracuse, which was a great way of learning from feedback, but not just doing the research, but also engaging with the community. And I know what you're thinking, where are the frontline communities here? I actually did focus groups at the local YMCA, and I learned a lot when I'm showing European standard bicycling design, and the reaction to that was, this is communism, this is not us. And it's very interesting to see the American perspective on sustainable mobility versus driving a car. There's a lot to learn there. Okay. Finally, this is my personal topic of passion and everything that is who I am right now, the hill I will die on, which is aerial diagnostics, the use of drones in building performance inspection. This project starts with the realization that we are living in aging built environments. The moment a building is built, it's immediately aging. And so we have to be aware of how to maintain it. We're very good at maintaining building systems. We can go and fix an HVAC and lighting systems, but the building enclosure is something that's typically overlooked. And this project started here and transformed into a funded project by the Department of Energy called AIR-BEM, Aerial Intelligence for Retrofit Building Energy Modeling, where the process was designed that we use drones to collect data, all the way to do energy modeling to understand the performance of the building enclosure. But before I go into the details, which I will, I want to introduce the team for you because I want to show you how architects were leading and collaborating with engineers. So the team I was leading had 2 PhD students and 1 postdoc. Yasser is now lead, don't tell him I forgot to, lead simulation strategist at my company. Kaiwan is professor at University of Alabama University of Alabama, sorry, civil engineering. Senem couldn't be here today because she had teaching engagement, but Senem is my partner in crime. She is faculty at the College of Engineering and Electrical Engineering and Computer Science. She had 2 PhD students with her. And also Dr. Ed Bogish, who was leading the Syracuse Center of Excellence at the time, was an expert on the team on tech-to-market experiences. And at MIT, Professor John Fernandez was leading issues of climate. With him was Norhan Bayoumi, who's a postdoc scholar now, Mohannad Al-Khouli, who is undergraduate, then master's, and now working in the company as well. And we also had Sandeep Ahuja, who leads Cove architecture, previously Cove tool. So you can see that this is a conversion team. That was really the case of developing these kinds of technologies. So how does it start? Basically, we collect data by traversing building envelope components systematically. And we're collecting data in 2 types. Regular RGB images. These allow us to identify things like windows and walls and where the roof is. The AI is trained on thousands of images that know that this is a window. That is a trivial problem. It's really not that difficult to have an AI identify a window. Where it becomes really problematic, very difficult, is to identify on thermal images where issues are with the built environment. And I will explain this in a moment. This is a typical thermal image. A thermal image will show you the thermal performance of the building enclosure. It can show you that there is leakage of air. It can show you that there is leakage of heat. It can show you that there is water intruding into the surface. In order to be able to read this, you need to have a building science background. And so if you ask anyone to say, where is a problem here? They will tell you there is a hot spot or a cold spot. They won't really tell you what the performance issue is. And that was the project. We basically sat down, defined what are the issues that we can identify from both the RGB and the regular images and the infrared images. And this is a case, for example, right here. You can tell that there's something happening right underneath the window. And because it is under the window, this is most likely air that is leaking, in or out. Could be infiltration, could be exfiltration. And so we trained models on thousands of images to be able to detect these issues and then be able to map them onto 3D models. So this is a building at the Georgia Tech campus where we are showing the model, but also what is called 4D representation of thermography if we're taking a series of time images. And this is where we're able to, on the 3D thermography, identify where infiltration, exfiltration is, or where thermal bridging is, or where water intrusion, or where there's cracks, or all of these issues autonomously. And that is key. Basically, the computer vision, or the AI, is allowing us to tell where the issues are based on the training. And then we translate this geometrically into simulation models that allow you to know the impact of any decision you will make on the building enclosure. And in that sense, we pioneered the field of aerial building envelope diagnostics. And of course, it became very interesting to pursue this further. But I know what you're thinking. Where are marginalized communities from that? We took the drones to Grove Park and other communities because the data we were collecting and we were labeling are not inclusive of frontline communities. We actually had to collect data in African American communities and label them so that the images are not just biased towards standard construction, it's also showing severely derelict building performance. And we went also to their middle school, the John Lewis Invictus Academy. They came to us and we went to them to show them what thermography and technologies can be to help in their career decisions. And this is when we went to the school. You can see the roof over here. There's a roof and the students are looking at it. There's a drone right here and the students are looking at it. And this is a demonstration. Of course, it was later in COVID where I brought toy drones to explore with the students. So the first student is actually shy and afraid of the drone, like doesn't want to deal with it. So I give it to the second student who was immediately eager to do it, like ready. The third one is doing it, and then the first one now is curious. And that's exactly why we wanted to bring these technologies to the classroom, so that those who are even afraid of them can have an insight and an in onto what this can open up in their lives. So I'm going to now show you what this kind of research led to for the creation of a startup. That is the reason why I'm actually back in Syracuse. So the first thing, I got this Regent's Innovator title, and they gave me a 3-year leave of absence that is extendable to 6. And the first thing I did was come back to Syracuse. So that tells you how much I like being here. So what we're doing at Lamarr, which is the company, the startup, is we're automating building exterior diagnostics for both retrofitting and new construction. And we are a startup that is spun off from research at Georgia Tech, MIT, and Syracuse University. And now I get to tell you the kind of ways I engage with people on this. Because when I want to engage someone, I have to give them some numbers. And so buildings account for 37% of global carbon emissions, that's fine, but the building envelope, the enclosure, is key when it comes to these kinds of carbon emissions. There's $100 billion that are wasted annually in the United States by defective envelopes. But on the upside, according to the Department of Energy, we can reduce energy up to 35% through envelope retrofitting. And we have a significant opportunity with carbon emissions that can be saved. And according also to the Department of Energy, it is a high return on investment because it amplifies the impact of any other retrofit we do. So let's say you're in a building that has HVAC issues and you want to upgrade the system. If the building enclosure is vulnerable, you're upgrading the system and you're going to lose all of the energy to the outdoors. So if you want to get to net zero targets, it's not possible without the radical reduction in the time and cost of envelope diagnostics to identify the opportunities of getting the best return. So the problem with inspections in general when it comes to the building enclosure is that they're slow. If you want to inspect Slocum, you will have to have someone walk around it, then possibly climb it. Then how do you get access to the roof? And how, after all of this, you stitch all of the data, you have how many people doing this, and even if you're using drones, somebody has to sit down and sift through every single image. Also, it's prone to errors. There are technologies that are used, something called the blower door test. The blower door test is a test for pressure. It will not tell you where the issues are or what they are. It's just going to tell you if the building is pressurized correctly or not. It's clunky, it's invasive, it doesn't scale. You can't do it on multiple buildings. And finally, it is a costly approach because it's going to take a lot of money to start, but also a lot of time. It will take up to 12 weeks to get any feedback on a 100,000 square foot commercial building. And according to the General Services Administration, which is the owner and operator of all federal buildings, they receive their envelope reports in 6 months to a year. So it's really significant to address this issue. And so at Lamarr.AI, we are like giving a building an MRI as a metaphor with automated diagnostics. So the same way the MRI changed humanity, what we're aiming to do is to transform the built environment from a health monitoring perspective. Our solution is basically what I explained to you is drones with thermal imaging and the proprietary AI that makes this process 5 to 10 times less costly, 10 times faster, and 50% more accurate. And we know these numbers because we've done the research. We actually did that through the Department of Energy project. And we know that the same 100,000 square foot commercial building, we can give you a report in less than 3 days. So we've developed this unmatched edge through the proprietary AI that does two main things. The first is we're able to classify defects and map them onto the models. The second thing is we do accurate building energy model that allows for return on investment assessments. So the way we do this is we collect data anywhere. We are not a drone company. We actually work with drone operators across the world. We're deployed in North America, so Canada and the US, in the UAE, and in the UK, and more. And we're collecting this data, doing the energy simulation, then we're giving the surgical retrofit recommendations, and that's key. Because if you get anyone to give you recommendations for the enclosure, it's going to be mostly overhaul. We do very surgical things. And then we've developed this into several approaches. Lamarr Detect is our primary product that scales to hundreds of buildings. So we can fly the entire Syracuse University campus, of course, in weeks. And then with every data we get for the building, in 2 to 3 days, you'll get a report about the building. Then we do the second tier is diagnose, where you learn more about the cost of retrofitting. And finally, Lamarr Audit is the energy modeling that gives the return on investment analysis. And so we approach different opportunities differently. And this is the representation of it. So in Lamarr Detect, you're getting a 3D model with the anomalies mapped onto it. With diagnose, you get the retrofit work plans and costs. And with audit, you get the energy simulation and the return on investment. The solutions are built for 2 cases. With existing buildings, it's compliance and ESG, retrofit planning and ROI analysis, and pre-acquisition due diligence. If someone is acquiring new buildings, we can help them in assessing how these buildings are performing before they occupy them. But very interestingly, new construction. We're able to help buildings who are currently under various stages of construction to verify how they came together. And actually in the UAE, for example, we come after water testing, so they put water on the roof to see if the roof is leaking, and we do the thermal scan after that to see, did the water actually get retained in the roof or anything like that. So we're able to help with new construction as well. So I'll show you some examples so you get to see how this works. This is a university building where we're translating these envelope defects to decisions. This is what's called the net present value cost curve that is comparing doing nothing versus retrofit scenarios. We're enumerating the number of failing windows, water damage, insulation defects, and physical damage, and mapping this onto the 3D model. So you're seeing where everything is and you're able to make decisions on it. And then of course we give metrics for savings and the return on investment, etc. And because we're a building science founding team, our recommendations through the AI are surgical. So this is a historic building. We don't say just add insulation, it's historic mortar repointing because this is where we are here. This is water damage and how to address it. This is a university in the UK where the facilities manager knew that they needed to replace the roof, but they didn't have the means to communicate this to their executives. So we were hired to do the roof inspection and the building as well. And because the roof is reaching 15% of water damage, that immediately makes it viable for a roof replacement. Finally, this is our first customer ever. This is a building portfolio assessment in Tampa, Florida. These are 12 buildings that we're about to acquire. And we were able to tell them, your worst performers are these 3 buildings because they have the highest thermal anomalies as compared to the HVAC impact. So if you're focusing on fixing buildings, these are going to be your high priority. So I want to, before I close, I want to introduce the team that you saw already in the research. Just to give you context that everyone who worked on the research from the leadership perspective did get to enjoy commercializing this work. So Nurhan, who was a postdoc, is now the CPO. John, who was a co-PI, is now the Chief Strategy Officer. Senem is our CTO. And we had, oh, this is a terrible picture for Ben. But basically he did the strategy and business development. So why did we name the company Lamarr? How many of you know Hedy Lamarr, the actress? Good? Oh, wow. Great. Well, typically I don't get any hands. Hedy Lamarr was a beautiful actress in the 30s and 40s, but she was also an inventor, and she was not known for it. She invented signal hopping technology, which is the basis for Bluetooth and Wi-Fi encryption, and was used in World War II communication, but she never saw a cent from all of the patents. So we dedicated the name of the company to all innovators who did not gain prominence for their inventions during their time, especially women like Hedy Lamarr. I'd love to end here, but I just want to add one more thing, that it was all about design scholarship community to get to this, and that's what I highly encourage all of you as students in your time at Syracuse University, because these students who are from Syracuse University, the lab was called the PEOPLE, the Performative Praxis Lab, and these students who are at Georgia Tech are the reason why you're able to see all of this. There is a community of scholarship that you can be part of, and you will see amazing things. While you are learning how to be a designer and while you are doing studio work, you can also do impactful research work. This is the team. I'm showing this picture because this is Rawad. Rawad was a Master's of Science student here at Syracuse University, joined me at Georgia Tech and did a Ph.D. And it's really very exciting to see that these trajectories do exist and start at Syracuse University. This is the team, of course, in an AI-generated format. And finally, I'd like to thank you so much for your attention and happy to take your questions.
Thank you so much. That's amazing, amazing work. I love two things I just want to start off with before I'll open it up for questions, which is the title, From Studio to Startup, which is great. I love that you started with the studio experience and ended with it as well. So maybe if you could just say a few more words about the role of the architect in maybe the students, actually, like thinking about how many of you are interested in these design research projects or joining something or starting something up on your own. What do you see is the advantage of the architectural education in a lot of this work? And as you continue and working with teams, data scientists, engineers, how does that experience really contribute to those teams?
Absolutely, thank you for this, Beth. So design education, studio culture in general, is very unique as compared to other research units in general. And so when the students are typically in the studio dealing with significant stress, whether it is from the demands of the program or the architectural design education approach, professor demands, etc., pressure, peer pressure, all of these things, you're building bonds together and you're getting very, very close in terms of the camaraderie. And that is how actually I was approached first with the solar decathlon here. Students came and said, we want to do the solar decathlon, but it was the build project. It was much more challenging and it didn't pan out. But these same students did do competitions together and went out, did masters after this, master's degree, etc. Became actually Syracuse University Scholar. That's what it's called, right, for students. The design studio culture is unique in such a way that you don't have to do anything individually. And so if you are working together on an external competition, if you encourage professors to bring external competitions, or if you are working on a research problem with other researchers across campus, there's a lot of seed opportunities. If I'm not mistaken, Syracuse University helps with that a lot. It's quite unique, that kind of education, and you should definitely capitalize on it if it is of interest to you to do that kind of research.
Questions?
Hi, is it working? Okay, awesome. So you had some really amazing research ambitions encompassing things like sustainability, societies, technology, efficiency, etc. My question is, what made you choose architecture as the field to pursue all this research?
Oh, that's great. Thank you so much. Okay, so the question is, why did I choose architecture? I started off saying I wanted to do computer science, and then I went to engineering school in Cairo, and I attended one lecture, and I was like, I don't want to do computer science immediately, and I decided that I do like programming, but it's not the thing. I don't want to learn that. And I wanted to experience life in general, and spatially, architecture just made so much sense when it comes to impact on our lives. I wanted to have a tactile experience with life. And so when I went to architecture school, I didn't know why I went to architecture school really. I was like, I want to do something with design, etc. In the second year, I took a course, it's titled here Building Systems. It's environmental control back then. That changed my life immediately. Knowing that a decision in a building can change your comfort, your perception, the amount of money we pay in an energy bill, etc., that really motivated me to pursue that, and then it grew through it. I did not go into architecture thinking I'm going to use drones at all. As a matter of fact, drones came after the Ph.D., just so you know. Hope that helps. I'm sorry.
Nice to see you.
Yeah, great to see you too.
I'm curious about how this is impacting not only how you teach, but how architecture is taught at Georgia Tech, and maybe, I don't know if regionally, or how you see these kind of efforts, the interdisciplinarity of your teams in ways that could have strategic impact in architectural education and the future of educating future architects.
Thank you for this very much. We happen to have a culture at Georgia Tech of engaging communities as much as we can. And so when I came with the idea of let's engage this community, there was almost like no resistance. I actually do it, like be embedded, do all of these things. With studios, it has to be like the ULI Heinz competition, you're aware of that. That is like a cultural thing. Like you have to actively want to bring it. It's very different than when the students bring a design competition. So at Georgia Tech, the research that leads to engagement with communities allows us to do design studios and courses that engages with these communities. So with Grove Park, it started off with saying, let's help in designing a building at, in the Solar Decathlon design competition. And then I came to them and I was like, we can do research together. We can apply to funding together. And then coursework was welcome then. It's a process of just starting, basically making sure that you don't go to a community without knowing who can help in the leadership of the community, and that helped a lot. But Georgia Tech has a culture of that, to be honest.
Yeah, thank you for your interesting presentation. My question is about the accuracy of AI. When I talk with AI companies and AI project teams, they are struggling about the accuracy of the AI. So my question is, what strategies can improve the accuracy of the AI when predicting long-term building performance under climate change conditions?
That's a great question. Thank you so much. We get that question a lot because everyone uses AI sparingly. When we were developing this research, we were only focusing on accuracy and recall, which are the two measures that we were using. And we got to 90% accuracy before we went to commercialize the work. And the way we conduct ourselves when it comes to like regular checks of accuracy is highly academic in the context of industry. So our CTO, who is an academic, has her hands in the fire with publications and always making sure that she's at the cutting edge through the conferences, has the engineering team continuously monitoring the accuracy of our work by doing annotations. So the whole AI thing is about the training of the data. And so we do our own training, and then we compare that output scientifically, and then basically make sure that the accuracy is reliable. With other companies, and if you're talking generally about accuracy in AI, it's a question that you have to ask with whoever you're working with. How are you validating your accuracy? With us, it was publications. We do peer-reviewed publications, and we make sure that we're always at the forefront of this kind of technology. Thank you.
There's another question.
Thank you for this speech. I really like your whole concept of how you went from the studio to a startup. I was just wondering, what's your advice to people, especially younger students, who want to get involved in startups and potentially create their own company that intersect between architecture and tech?
I'll tell you exactly what happened with one of my students, so I'm not going to point out. She's in the room here. You have to go to someone that you're interested in working with and tell them, I would like to find out how I can work with you. And then it's going to be a match, because you might find that the dynamic doesn't work. But in order for you to break that kind of silo that you would be in, you have to find out who you would like to, who you've seen the trajectory of and you would like to talk to them. As an undergraduate student, there is not just a lot of energy, but there's also the eagerness and excitement. And many people will welcome that. My advice is, the moment your work becomes valuable, make sure you get paid. That's it.
Thank you.
Of course.
Good advice. Maybe time for a couple other questions if we have it. Yeah, Brian.
Hi, Tarek. Thank you so much. Hi. In terms of AI, as you were mentioned before, it's kind of there's the branding aspect of it as well, and in that you've been working with machine learning for a while, I just thought it'd be helpful if you reflected a little bit on the relationship of your work to generative AI, to machine learning databases, what kind of neural network models you might be using for the work if that's not proprietary. But just to kind of, I think, certainly contextualize it within the rhetoric of AI today.
So the AI we have developed as a core technology is based on computer vision and machine learning. The generative AI component is the retrofitting recommendations that we have been developing through large language models, where we feed all of the retrofitting design technologies, opportunities, techniques, etc., and make sure that it's tailored to the context of every anomaly that we find. This is where it becomes, let's say it needs continuous review, because computer vision, we know the percentage probability and accuracy. When it says this is probably water intrusion, you can see it with your own eyes and it's done. You can, but if you have the expertise, you will know. But with generative AI, when it comes to solutions of how this can be addressed, this is where it's challenging. And that is something that we're embedding design logic into that, and that is not a trivial problem. This is where we're focusing right now on that. Because at the end of the day, we want it to be automated so that you're able to see, like, here's the anomaly on the 3D model, here's how to solve it, here's how much it will cost you, this is the return on your investment. That how it's going to be solved needs a moment. Does that make sense? Yeah.
Hi, thank you so much. I'm curious on how, on a broader scale beyond looking at just the building, but how if the climate changes from where you're building, how that data is inputting into the software and the programming, and if it changes based on different climates.
Thank you for this. The approach for understanding buildings as they are constructed depends regionally on where you are. Its response to the climate is something that is very important, and we contextualize this based on where we are geographically. How the data is collected all the same, but how to respond to data and anomalies that were identified in Dubai is very different than in Toronto. And that is where the opportunities of generative AI come through. But we have been focusing on American construction. Scaling to other countries takes a moment, of course, because it all has to be contextually driven. Does that help with the question? Okay.
Thank you for your presentation. Very inspiring. So my question might be a little bit technical, but so you explained very well that you would be able to detect thermal anomalies qualitatively, I would say, and classify what class of anomaly your building is characterized with. The question is that are you or the company have the technology to be able to quantitatively say what is the extent of infiltration, exfiltration, or airtightness? Yes or no? Can you please also explain how you would translate the detected thermal anomaly into a form of post-process information that you use as an input for your energy model? Thank you.
Thank you for this. It is technical. I'll answer straightforward. So we do, the detection of the anomalies is qualitative. The quantification is typically done through a trial and error process that we have been working through when it comes to the severity of the qualitative representation. Sometimes you will see that this is a severe issue as compared to barely visible issue. This is where it comes through. When it comes to the translation of this to numerical inputs, we have the proprietary part here is how do we translate it to infiltration, exfiltration in thermal zones, and how we translate this to R-value reductions in the insulation. That is the research that we published on, and I'm happy to share these resources afterwards. Does that make sense?
Nina.
Thanks for the great presentation, Tarek. I have a question about the underserved communities where you did the retrofit projects where you kind of had to spread the budget out quite thinly. I'm very curious to know, this is such an important topic of affordability in retrofits.
Yes.
How do we go about obtaining resources, unlike in the UK and the EU, where there was a heavy amount of government subsidy in the kind of the recent retrofit movements like Energy Sprong and so forth? We don't have that here. And so I wonder if you thought about or if you had the opportunity to do any kind of sensitivity analysis or any kind of post-occupancy evaluation of the projects to see, you know, I'm always thinking about what do we learn from this? How do we now integrate this into the way that we think about and practice retrofits? Were there any kind of useful lessons learned or any data that you were able to get through modeling or survey or otherwise that you found you could take forward?
So thank you for this. Multiple layers that I would like to address. The first is, yes, we did post-occupancy after the retrofitting, and we published on it. If you look at Google Scholar, it's one of the most recent publications of ours. It's led by Anuranda Kadam, Anu, and you will see the very interesting finding is when we did these retrofits, we did not get to the standards that are required by, let's say, ASHRAE or whatever kind of standardized institution. We did not reach them. We could not reach the air tightness that's required, but people were happy. And that is really a huge difference. So their energy bills went down and they felt more comfortable. And so not reaching the standard is not an excuse to not do affordable retrofits. So that's the first layer. The second layer is the funding we got was from a very particular situation. It's called the Partnership for Inclusive Innovation, and it's a research unit within Georgia Tech, and it gets funding, and then it does research projects, and you're able to use these to experiment. Based on that, communities were able to apply for other sources of funding, whether it's local, state, or federal. There's weatherization programs coming from the Department of Energy that the communities need evidence for. So how we're able to help from a research perspective is embed ourselves in the community, understand it, do the research, write the reports, and then help this community in filing for weatherization programs. There is in NYSERDA in New York State is huge on that, so you can help that way for sure.
Michael.
Yeah, thank you for coming, Tarek. It's
thank you for inviting me.
Here. Just a quick question. Maybe this should have come earlier, but why are you here? No, I mean that literally. So you have a leave.
Yeah.
Just maybe briefly, what do you hope to accomplish?
Sure.
Let's say on this leave, and will you come back and do some more things with us?
Thank you, Michael. So I'm here because Lamarr has been selected for a program called Genius New York. Genius New York is, this is according to them, okay? The largest uncrewed systems and robotics accelerator in the world, and it lives in the biggest incubator called Inspire. It's a building that opens next week, which is the biggest incubator in New York State. And they're giving us an investment, they're giving us advisors, they're giving us a whole program, and they're giving us office space. So I'm here, and other members of the team are coming here because for the next year, we're really focusing and we're scaling and we're really growing the company that way. I'd be very happy to be engaged with Syracuse University. As you know, Michael, you said, would you like to come? I was like, immediately, yes, absolutely. Yes.
Great, thank you so much. Amazing work, great to see, and we'll look forward to the presentation next year.
Thank you. Oh yeah, we have, in May, we will have is that open to the public? I don't know. They have a Genius New York showcase thing, and if we win, we get more investment. I will let everyone know.
Fantastic.
Yeah.
Thank you.
All right, thank you.